Spectra. Hot objects emit electromagnetic radiations such as infrared, visible light, and ultraviolet. And spectra can be classified into two types. The first type of spectra is called emission spectra, and the second type of spectra is called absorption spectra. Emission spectra. There are two kinds of emission spectra. The first is continuous emission spectrum. The light emitted by tungsten wire lamp and the sun forms a continuous color spectrum. By using a diffraction grating, a continuous spectrum is formed on a screen, as shown. Another kind of emission spectra is called light emission spectrum. The light emitted by a monoatomic gas at low pressure form a light spectra. Examples are hydrogen gas, neon gas, or mercury gas. The light spectrum can be captured by a screen, again by using a diffraction grating, as shown in the diagram. Let's see the physical processes for the formation of light emission spectrum. First, we have a discharge tube containing a monoatomic gas at low pressure. When the discharge tube is connected to a EHT, a light spectrum is formed by using a diffraction grating. How is the light emission spectrum formed? First, different gases have different sets of energy levels. Consider three energy levels E1, E2, and E3. With N is the nth energy level state, where N equal to 1, 2, 3, etc. When the electron in level 1, N equal to 1, absorbs an energy E equal to E2 minus E1, it will excite to level N equal to 2. However, the electron in the excited state is unstable. When the electrons make a transition from N equal to 2 to N equal to 1, a photon of energy E equal to E2 minus E1 and frequency F equal to E2 minus E1 over H Planck's constant is emitted. Since the energy levels in the atoms are discrete, therefore the photons emit have definite energy E, imply the photons emit have definite frequency or lambda. Therefore, a light spectrum is observed as shown. Note that, first, since the energy levels are discrete, the electron or the atoms can only be excited to a higher energy levels by absorbing a certain amount of energy. Second, different gases have different sets of light spectra because the patterns of energy levels of the gases are different. Also, you must notice that light emission spectrum is bright light shown on a dark background. Example 1. The energy of the photon emit E equal to HF equal to Hc over lambda. H is 6.63 times 10 to the power negative 34. C is 3 times 10 to the power 8. Lambda is 434 times 10 to the power negative 9. Therefore, the energy of the photon emit will be equal to 4.58 times 10 to the power negative 19 joules, which is equal to 2.86 electron volt. Part B, we have E naught minus En equal to E, implying E naught minus negative 3.4 equal to 2.86. Therefore, the initial energy level E naught equal to negative 0.54 eV. Example 2. The energy of photon emit equal to HF equal to Hc over lambda equal to negative 0.54 minus negative 3.39 times 1.6 times 10 to the power negative 19. Therefore, the wavelength of light emit is equal to 4.36 times 10 to the power negative 7 meter. Example 3. First, we draw energy levels E1, E2, and E3. When the atoms returns from level E3 to E1, the photon emit has frequency F3. Therefore, we have E3 minus E1 equal to HF3. Similarly, when the atoms returns from energy level E2 to E1, it emits another photon of frequency F2. Therefore, we have E2 minus E1 equal to HF2. Now, if the excited atom returns from E3 to E2, then we have the energy of photon emit is E3 minus E2, which is equal to H times the frequency of photon emitted. We call it F. From these two equations, we get E3 minus E2 equal to H F3 minus F2. Therefore, comparing these two, we got F equal to F3 minus F2. Example 4. Again, let's first draw the energy levels E1, E2, and E3. When the excited atom returns from E3 to E1, a photon of wavelength lambda 1 is emitted. Therefore, we can write down E3 minus E1 equal to HF equal to HC over lambda 1. Next, when the excited atoms returns from energy levels E2 to E1, another photon of wavelength lambda 2 is emitted. Therefore, we have E2 minus E1 equal to HF2 equal to HC over lambda 2. Now, if the excited atom returns from energy level E3 to E2, we have E3 minus E2 equal to HF3 equal to HC over lambda 3, where lambda 3 is the wavelength of photon emitted. By using these two equations, we have E3 minus E2 equal to HC 1 over lambda 1 minus 1 over lambda 2. And comparing these two equations, therefore we got 1 over lambda 3 equal to 1 over lambda 1 minus 1 over lambda 2. A gas atom can be excited from energy level EM to EN by bombarding the gas atoms with an incoming energetic electron of kinetic energy E. In the diagram, we have initially an atom in the energy level state EM. When an energetic electrons bombard the atoms, if the kinetic energy of the electron is greater than or equal to En minus Em, then electrons can transfer sufficient energy for the gas atom to be excited. That means excitation is possible. However, if the kinetic energy of the electron is smaller than the energy level difference En minus Em, then excitation of gas atoms will never happen, because the incoming electron does not have sufficient energy to excite the gas atoms. Example 5. The energy level difference between E3 and E1 is equal to E3 minus E1 equal to negative 1.5 minus negative 13.6, which is equal to 12.1 eV. When the hydrogen atoms in energy level E1 are bombarded by electrons with kinetic energy E, the gas atoms can be excited from energy level E1 to energy level E3 only if the kinetic energy of the electrons is greater than that of the energy level difference, which is equal to 12.1 eV. For part A, since the kinetic energy of the electrons is only 10 eV, which is smaller than 12.1 eV, therefore, excitations of hydrogen atoms is impossible. For part B, the incoming kinetic energy of the electrons is 12.5 eV, which is greater than 12.1 eV. Therefore, 12.1 eV of Ke of the electrons is transferred to the atom in order for its excitations to E3. And the Ke of the incoming electrons becomes 12.5 minus 12.1, which is 0.5 eV after the collision. A gas atom can also be excited from energy level Em to energy level En by bombarding with a photon of energy E pi. If energy of the photons E pi is equal to the energy level difference En minus Em, the photons is absorbed by the atom and excitation of gas atoms occurs. However, if energy of the photon E pi is smaller than the difference of energy levels En minus Em, excitation of gas atoms will never occur. Example 5. In order for the atoms to be excited from E1 to E3, the energy need is E3 minus E1, which is equal to negative 1.5 minus negative 13.6, which is 12.1 eV. In order for the atoms to be excited from E1 to E3 when bombarded by photons with energy E pi, the energy of the photons must be exactly equal to the energy level difference, which is equal to 12.1 eV. In both case A and case B, in case A, the energy of the photons 10 eV smaller than 12.1 eV. In case B, energy of the photon is 12.5 eV, which is larger than 12.1 eV. Therefore, in both case A and B, excitations of the atoms from level 1 to level 3 is impossible. Only in case C, the energy of photon is equal to 12.1 eV, which is equal to 12.1 eV, the energy needed to excite the atom. Therefore, excitation in case C is possible. Part B, absorption spectrum. How to produce an absorption spectrum when a white light source which produce continuous spectrums, a sealed tube with bromine vapor, and a diffraction grating is arranged as shown. An absorption spectrum will be seen on the screen. Note that absorption spectrums means we have dark lines shown on a continuous spectrum, which we call shown on a bright background. Also, light emission spectrum and absorption spectrums are complementary. Let's see the physical process of producing absorption light spectrum. White light consists of photons of a continuous range of energy E1 pi, E2 pi, E3 pi, E4 pi, E5 pi, and a continuous range of frequency also, with frequency f1 pi, f2 pi, f3 pi, f4 pi, and f5 pi. When the photons of a certain energy E pi, for example E4 pi equal to hf4 pi, is equal to the energy difference of the cool bromine atoms, that is E4 pi equal to hf4 pi equal to E2 minus E1. These photons would be absorbed by the bromine atoms, and the bromine atoms go to the excited state. Hence, only the photons of frequency f1 pi, f2 pi, f3 pi, and f5 pi can pass through the bromine atoms and traveling in the original directions. Now, when the excited bromine atoms returns to the lower level state, that is from E2 to E1, a photons of the same frequency as absorbed, that means a photons of frequency f4 pi is emitted in different directions. For these atoms, the intensity of the light in the original directions, that is to the right, is decreases, which accounts for the appearance of the dark lines. Let's see Bohr's model of hydrogen atom. There are two postulates that define Bohr's atomic model of hydrogen atoms. First, the first postulate is that when the electrons circulate around the positive nucleus in certain orbit, it does not radiate energy. Or we say, when the electrons circulate around the positive nucleus in certain orbits, it is stable. Second, the angular momentum L of an orbiting electron is mv_r, where m is mass of the electron, v is the speed of the electron, r is the radius of the electron from the nucleus. And the angular momentum of the orbiting electron is an integral multiple of h over 2 pi, where h is the Planck's constant. That is mvr equal to n h over 2 pi, where n equal to 1, 2, 3, 4 represent the energy level state. In a hydrogen atom, the electron circulates around the nucleus or the protons with speed v, as shown. The centripetal force on the electron, F equal to mac equal to mv squared over r, is equal to the electrostatic force, E squared over 4 pi epsilon r squared. Since the angular momentum of the electron, mvr equal to n h over 2 pi, from equation 1 and 2, we got the radius of the nth orbit is Rn equal to h squared epsilon over pi m e squared times n squared. Notice that the radius of the electron in the nth orbit is proportional to the square of n. Example 6, we are given that R1 is equal to A naught. Then what is R2 and R3? Because the radius R is proportional to n squared, therefore we have R2 over R1 equal to square of 2 over 1, which is 4, imply R2 equal to 4A naught. Similarly, R3 over R1 equal to 3 over 1 square equal to 9, implying R3 equal to 9A naught. The energy of an electron in a hydrogen atom is a sum of its kinetic energy and potential energy. By E equal to Ke plus Pe, we got the energy in the nth level is equal to negative me e to the power 4 over h squared epsilon squared times 1 over n squared, where me e to the power 4 over h squared epsilon squared equal to 13.6 electron volt. Therefore, we have the energy of the electron in the hydrogen atoms in the nth orbit is equal to negative 13.6 over n square eV, where n is called quantum number, and n has number 1, 2, 3, 4, etc. Notice that En is called energy level. For n equal to 1, we have the energy E1 equal to negative 13.6 over square of 1 equal to negative 13.6 eV. For n equal to 2, we have E2 equal to negative 13.6 over square of 2 equal to negative 3.4 eV. And for n equal to 3, we got E3 equal to negative 13.6 over square of 3, which is equal to negative 1.51 eV. Notice that the greater the quantum number, the greater the value of energy level. What are meant by excitation potential and excitation energy? The excitation potential or the excitation energy are the potential or energy required for an atom to be excited from a lower energy level to a higher energy level. The first excitation potential or energy is the potential or energy required to excite an atom from n equal to 1, that is from the ground state, to n equal to 2, that is the first excited state. The second excitation potential or energy is the potential or energy required to excite an atom from n equal to 1, the ground state, to n equal to 3, which is called the second excited state. Then what is meant by ionization potential or ionization energy? Ionization potential or energy is the energy or potential required to ionize an electron from the ground state to infinity. That is, the electron is free from attraction by the positive nucleus. First excitation can be shown in the diagram, and second excitation can be shown in the diagram. Ionization process can be shown in the diagram. Example 7. A. Ground state is the most stable state, or we say ground state has the lowest energy level state. Which is equal to negative 13.6 eV. Part B, the first excitation potential is equal to negative 3.4 minus negative 13.6, which is equal to 10.2 volts. And the first excitation energy is equal to 10.2 eV. Similarly, the second excitation potential is equal to negative 1.5 minus negative 13.6, which is equal to 12.1 volt. And the corresponding second excitation energy is equal to 12.1 eV. Finally, the ionization potential is equal to 0 minus negative 13.6, which is equal to 13.6 volt. And the corresponding ionization energy will be equal to 13.6 eV. Interpretation of light emission spectra of hydrogen atom. When an excited hydrogen atoms, as seen in the diagram, fall from higher energy level EB to lower energy level EA, a photon will be emitted with energy E. By En equal to negative 13.6 over n squared eV, we have, when n equal to A, Ea equal to negative 13.6 over A squared, and when n equal to B, we have Eb equal to negative 13.6 over B squared. Hence, the energy of the photon emitted, E, will be equal to Eb minus Ea equal to negative 13.6 over B squared minus negative 13.6 over A squared. Hence, we have Hc over lambda equal to 13.6 times 1 over A squared minus 1 over B squared. Example 8. When the excited hydrogen atoms falls from n equal to 2 to n equal to 1, by the equation En equal to negative 13.6 over n squared eV, we got the energy of photon emit E equal to 13.6 times 1 over square of 1 minus 1 over square of 2 eV. Therefore, equal to 13.6 times 1 over 1 minus 1 over 4 times 1.6 times 10 to the power negative 19 joules. Instead, energy of photon equal to Hc over lambda. By calculation, we find that the wavelength of light emitted lambda equal to 1.22 times 10 to the power negative 7 meter. For part B, we got the energy of photon emitted E pi equal to 13.6 times 1 over square of 2 over minus 1 over square of 3 eV, which is equal to 13.6 times 1 over 4 minus 1 over 9 times 1.6 times 10 to the power negative 19 joules. Using similar methods, we find that the wavelength of photons emitted lambda pi equal to 6.58 times 10 to the power negative 7 meter. For part C, if transitions is from n equal to 4 to n equal to 3, we got energy of photon emitted is 13.6 times 1 over square of 3 minus square of 4 eV equal to 13.6 times 1 over 9 minus 1 over 16 times 1.6 times 10 to the power negative 19 joules. Therefore, the wavelength of photons emit lambda double pi equal to 1.88 times 10 to the power -6 meter. The wavelength in A shows that ultraviolet is emitted. For B, it shows that visible light is emitted. For C, it shows that infrared is emitted. Note that for hydrogen atom, first, the transition from quantum number n larger than 1 to n equal to 1 will emit photons lies in the ultraviolet range. For the transitions from quantum number n larger than 2 to n equal to 2, will emit photons lying in the visible light range. For transitions from quantum number larger than 3 to n equal to 3, will emit photons lies in the infrared range.